Hi guys, welcome back to my channel. In today's video, we'll be discussing about the wave equation for potentials. So before I start this video, I assume that you already know the Maxwell's equation for both static and dynamic fields. I mean both the differential form and the integral form. If you don't know, just drop a message in the comment section. I'll make a separate video on this because in this video, I want to just focus on the wave equation for the potentials. Okay, so now let us assume that we have a charge of charge distribution rho and current distribution J. Now our aim in this video is to find both the electric potential V and the magnetic potential A. After finding these potentials, we can easily find the electric field and the magnetic field, which is given by these equations. Now how these equations are derived, I'll show in the coming time. So there are basically two important cases. One is the low frequency or the quasi-static case. In this, the source variations are slow and the range R is small as compared to the wavelength. So the fields may be approximated as the time independent case. This is a generalized case which we won't be discussing in this video. In this video, I'll be focused on the high frequency case, which is the second case. In this, the source frequency is high and the distance R is comparable to the wavelength. Here, the time retardation effects must be included because the fields propagate at a finite speed. So now we have two problems. We need to find the retarded potential, the V and A, and after finding that, we need to find E and B because we don't know whether this formula holds for retarded fields or not. So we'll derive both. So first, we'll look at the vector magnetic potential. Uh, we know that in both statics and dynamics, this equation holds true that the divergence of the magnetic field is zero. This is given from the Maxwell's equation. From the null identity, we can see that the divergence of a curl is zero. Hence, we represent this magnetic field as a curl of some another vector. That vector is the magnetic vector potential. So we define a completely new vector, which is the magnetic vector potential, and assume its curl is equal to the magnetic field. So since we created this own vector, we have the liberty to choose its own properties, which we'll be using this property in meantime. So this is the visualization of the vector magnetic potential, how it looks like. So now let's come to the electric potential. We know that in statics, the curl of the electric field is zero. This is given by the Maxwell's equation. Now from the null identity, we know that the curl of a gradient is zero. Hence, we can write the electric field as a gradient of some another scalar vector. This scalar, okay, not, yeah, this scalar vector is the scalar electric potential. But in dynamics, we know that the curl of electric field is not zero. That is, the del cross E is minus dou P by dou T. So there's a slight modification in this formula. We substitute the B is del cross A because this equation is valid for both statics and dynamics. So after substituting that equation here and doing some basic maths, we arrive at this equation. The new electric field is given by this equation. And the vector magnetic potential remains the same for both statics and dynamics. But for the time retarded fields, the electric fields gets changed. The new electric field is given by this formula and the magnetic field remains same. So this both equations we substitute in the Maxwell's equation, which yields the non-homogeneous wave equation given by this. So as I said earlier that we have the liberty to choose our own properties for this magnetic vector potential. We choose the del dot A to be the negative of mu epsilon dou V by dou T, that is the sum to be zero. This condition is known as the Lorentz condition. So under this Lorentz condition, if we simplify this wave equation, that leads to the following equations. So this is the simplified wave equation or the wave equation for potential under the Lorentz conditions. So these are called the non-homogeneous wave equation for the potentials. Now we'll find the solution for the wave equations because that will lead to our aim, which gives the scalar electric potential and the vector magnetic potential. So to find the solution of this wave equation, we consider a elemental point charge at the origin, and for simplicity, I assume spherical symmetry because in Cartesian coordinate system the calculation is too hectic. So I change the coordinate system. I come to the spherical coordinate system. So I take the advantage of the spherical symmetry. I assume the scalar electric potential to be V of r comma t. That is, it depends only on r. The theta and phi it is independent. And I assume the V of r comma t as some function of f divided by r, and substituting it here, that leads to a second order differential equation. Now we know that the general solution for this is of this order, and we find out of these both solutions we take only the time retarded part because that makes intuitively sense, because the electric fields can be time retarded, they cannot be added in time, so we just neglect this solution. Thus the final solution for this elemental scalar potential is given by this formula, where V is 1 by root mu epsilon. Now to get the whole retarded scalar potential, we just integrate over the whole volume of the sphere. So the final formula for the retarded scalar potential is given by this formula. So this shows the scalar potential depends on the value of charge at an earlier retarded time, that is t minus r by v. Similarly, okay, so this is the visualization of the retarded potential, how it looks like. So now similarly, if we solve the another equation, which is this, so that leads to the magnetic potential, the retarded magnetic potential to be more precise. So we have solved both problems. We found the retarded potentials, the retarded magnetic potential and the retarded scalar electric potential. Now after finding these both potentials, it is very easy to find the electric field and magnetic fields. The magnetic fields is given by the curl of the magnetic potential, and the electric field is given by this formula. So in this way, we find the potentials of the retarded electric fields and magnetic fields, and then by using the potential we find the electric fields and magnetic fields. Okay, thank you so much guys for watching this video.